I would like to go ahead and get started. And Brett, in answer to your question, yes, Janet just answered it too. You do have to click on the talk button. We'll get to that in a moment here. I'd like to welcome you all to the third in our series of 5 webinars, Connecting Scientists with Middle and High School Educators. Today's webinar features Sabrina Larson and Josh Ashline, who will be talking about freshwater aquatics. But before we get started, just a few reminders. Of course, use the chat. Well, let me back up just 1 second. As you can see, we're on the 3rd, and the 4th and 5th are yet to come. The 4th seminar will be on intertidal ecology, and the final one will be Why is Soil Important? There are a variety of folks that have joined us today that have been here all along. In other words, this is the 3rd session, and I think we're now beginning to feel very comfortable within this webinar platform. You can see that Janet is chatting a little bit with you. She is my backup, as you all know who've been here with us before. Janet will try to solve any problems as we go along that I can't help you with because I'm doing something else. So I'd like to just remind folks that we will be encouraging, of course, chatting on topic, please. And we will be answering, hopefully, any questions you have on today's topic. If you have questions while Sabrina and Josh are doing their presentation, go ahead and type them into the chat box. And we will be watching them. Janet and I will be watching them to make sure that if there's a way to go ahead and answer them right away. In fact, I think I recall Josh and Sabrina telling me that they would just as soon answer questions at the end of each slide. And so perhaps before we move on to each new slide, if you have any questions, either raise your hand there or go ahead and put something in the chat box, and we will make sure your questions are answered as we go along. At the very end of the presentation, we will encourage you to use both the chat box and raising your hand. You recall, I'm sure, that over in the participant box, you will see a little hand on the left-hand side of your screen. When you put your cursor over it, it will say raise hand. And when you do that, we will know that you have a question. When you articulate your question, you will need to punch the talk button, and you'll be able to see yourself talk via that line above. And as soon as you finish asking your question, please go ahead and unclick the talk button so that the presenters can answer your question. So with that, I would like to begin. Both Sabrina Larson and Josh Ashline are PhD students with Alaska Pacific University. Josh also works for the U.S. Fish and Wildlife Service, and Sabrina also works for the Alaska Department of Fish and Game. But that's about all I know about them. And so what I would like to do is turn the presentation over to both Sabrina and Josh, and I think they're going to want to tell you a little bit more.
Hello, everybody. I'm just going to make one quick correction to that. Neither Sabrina or I are either PhD students. We're both master students. As much as we appreciate you telling us, everybody, that we're PhD students, we don't want everybody to think that we're working on our doctorates and expect like really, really highly intelligent answers or anything like that. So just throwing that out there. Yeah, so I believe we just want to reiterate what Kathy said, that at the end of every slide, if you guys have questions, we're more than happy to answer them. We'd like to keep this as informal as possible as we progress through and talk about freshwater aquatics. I think Kathy had also mentioned at one point that she was going to have everybody else that's on here kind of introduce themselves and kind of tell us who they are, where they're from, and if I could request, maybe something that they find about freshwater interesting, just to kind of get this going, would be, I think, a great way to start.
Actually, Josh, thank you for reminding me to do that. Maybe what we'll do is I'll just do a little, I'll go down the participant list, and if everyone can just practice with the talk button, go ahead and just tell us something you're interested in regarding freshwater aquatics, or perhaps a freshwater a fresh body of water that you have locally. So let us go ahead and start with Lisa and her homeschool group. Go ahead and press the talk button.
As I'm on the phone for that, since we don't have it working on the computer, but I'm going to have I only have 2 students that have shown up, so I'm going to have each one kind of share their information. Trent. Your name?
My name is Trent. I'm homeschooled in 7th grade, and I'm totally been finding this.
Fresh body of water.
We have Lake Louise by our house, and Boy Scout, and Lake Gertrude.
Very good.
And?
My name is Brianna, but most call me Bree. I'm in 6th grade. And, yeah.
Body of water around the area.
I know there's one around my house, but I forgot what it's called. I have no idea what it's called. But I know it's around there somewhere. And yes, I'm...
Okay, Bree. Bree, if you remember it later, just put it in the chat, okay?
Okay.
And that's everybody from our site.
Thank you very much, Lisa. Let's move on to Brendan. Now, I know Brendan's on a telephone, and he may be having audio challenges. Brendan, you can go ahead and type something into the chat if you'd like. Just tell us where you're located, and also a body of water, fresh water, close by. Let's move on to Brett. Brett, would you like to? Yeah, it sounds like there are some mic issues. So I'm going to continue down the list. And if you have mic issues, just type into the chat. I'll move on to Corrine. Corrine, are you a student, an Environbond student with K. Shoemaker? Go ahead and just type that into the chat. So you can go ahead and click on the talk button and tell us who you are and where you're located. Okay, there she is. She is in Juneau, and I'm glad that you're connected here. When it's your turn to talk, Corinne, you must go ahead and punch the talk button right under the audio and video box there. So let's move on to Emily. Emily, tell us where you are and a body of fresh water close by to you. I think we're having a few issues with the mic. Okay, Emily's going to type it in here. And while Emily is typing, let's move on to Helen, if you would mind telling us where you are in a fresh body of water close to you.
Hi, I hope you can hear me. I'm in Noatak. Can you hear me?
Yes, we can, very well.
Okay, good. I'm in Noatak, and I guess the Noatak River would be the fresh water.
Okay, great. We'll move on to Lyle. Lyle, I guess, okay, there's Emily.
Hi, sorry, the talk button was blocked. I'm in Kivalina, Alaska, and we're next to the Woolwich River and the Kivalina River that flow into the Kivalina Lagoon next to the Chutchisi.
Great, Lyle. That's a little reminder to all of us. We have to unclick the talk button when you finish talking, otherwise no one else can talk. So we'll move on to Meg.
Hello, all of you. Can you hear me? Yes.
Yes, go ahead, Meg.
Oh, great. That's wonderful. Yeah, this is Meg Burgett. I'm out here in Wasilla, and I guess the closest water body is 8 Mile Lake, and the Little Susitna River is just right around the corner.
Great, thanks very much. We'll move on to Shannon.
Hey guys, my name is Shannon. I'm a senior in high school, and I'm one of Kay Shoemaker's Envirothon students along with Emily. I live in Fairbanks, and the two bodies of water that I'm thinking of that are freshwater are Quartz Lake and Birch Lake, although those are both about an hour away. I also have a friend, Halby, who's on our Envirothon team, who just joined, and he's going to jump on about 4:30, and he lives in Healy, and he's actually done, I think, a 10-year study on freshwater invertebrates, but he'll have to clarify, but he has a lot of knowledge, and I'm excited to have him on this team, and especially doing aquatics.
That's great, Shannon. Tell me his name one more time. Okay, thank you, in the chat. We'll move on finally to Zach.
All right, I'm Zach. I'm from Noatak. We have the Noatak River right on our village. And I'd probably like to know more about like freshwater activities that I could do with my science classes. I'm a science teacher up here for middle school and high school. But yeah.
All right, thank you very much. Okay, I think at this point we will go ahead and turn it back over to Josh and Sabrina. And I'd like to, make sure that you do ask any questions you have at the end of each slide, and Josh and Sabrina will answer them. Thank you. It's all yours, guys.
All right, well, thank you guys for giving us that information. We're really excited
to start our talk tonight on freshwater aquatics. And so why don't we go ahead and go to the next slide.
So what we want to do is give you guys a little background information about us, the scientists that you're being connected with, and who we are, what our educational backgrounds are, etc. So like Kathy said earlier, my name is Joshua Ashline. I'm a juvenile salmon ecologist with the United States Fish and Wildlife Service, the Anchorage Field Office. I started my career back at the University of Vermont in the early 2000s, getting a degree in fisheries biology. So I really specialize in the freshwater side of things. I've actually never physically worked with a marine system. Along those lines. And then first job when it was in Alaska, working with adult salmon. I've spent time all throughout the state of Alaska, working with both adult and juveniles out in Bristol Bay, the Aleutian Islands, the interior. And most of my work now is actually focused in the Big Lake watershed, which is just north of Wasilla. So Meg's probably very familiar with the area that I'm working in. And what we've been doing out there is kind of remapping the juvenile life history of coho salmon. So we tagged roughly 8,000 fish, about 55 millimeters, so just over 2 inches long, and tracked their movements throughout the freshwater systems for between 1 and 3 years. And basically found out where these fish are living in the summer, where they're living in the winter, what they're eating, how fast do they grow, how long do they spend in freshwater before they go to the ocean, and then we can actually capture them again when they come back from the ocean, so we can get some pretty decent survival rates as well. So that's kind of, you know, my career so far in a nutshell, and what we're in, my career in a nutshell. Moving on to Sabrina.
Hello, as Kathy said, I'm Sabrina Larson. I grew up in Northern California in a very small rural area, so the idea of using water, especially for farming and a lot of groundwater issues, is something that I grew up kind of listening to. And when I started college back in 2008, I was at the University of California in Davis, and I got my bachelor's degree in environmental policy analysis and planning. And I focused on water quality. And so basically I spent 4 years learning about all of the policy that goes with water usage, mostly with freshwater systems, also how that affects fisheries, and just kind of learning a little bit more about the hydrology side of things. And I started to get very interested. Sorry, I just saw the chat.
The chat's kind of distracting.
Yeah. So I started getting interested more in the salmon ecology side of things, and came up to Anchorage as a master's student in 2012. And I actually started doing a thesis project originally on the Kuskokwim River, doing more community-based watershed management work, and a little bit into kind of salmon health in the system. And unfortunately, that project did not actually pan out, which in science that happens quite often. And about a year and a half into my 2 years master's program, I switched over to do hatchery work, and that's what I've been doing since then. So I currently research maternal effects in Chinook salmon at the hatchery here in Anchorage. But I've also done quite a bit of work in British Columbia, not only kind of from the salmon farming aspect, kind of learning more about that, but also research at a hatchery setting there. And so although I don't really focus on researching freshwater aquatics as much anymore, I still enjoy going out and teaching field classes in the summer, just to kind of teach the new up-and-coming undergraduate researchers kind of how you do hydrology work in the field, and how that kind of connects to things like fisheries and also hatchery systems as well, because that is also interconnected. Before we go to the actual presentation, are there any questions for us pertaining to not only ourselves but our backgrounds? Okay, I'm taking that as a no. So if something comes up, thank you, in the chat. So if anything comes up that is immediate, write it in the chat. Like we said, we may or may not read it, but we'll stop at the end of every slide, make sure we didn't miss anything, and also we'll give you a chance to ask questions at the end of every slide. So we can go ahead to the next slide now.
So Sabrina and Josh, there was a question about seepage lakes and changing water levels, but why don't you wait and address that when you talk about lakes?
Okay, so the agenda, this is more just to show you kind of what we're going to be talking about. These are very broad terms and they correspond to the titles on the slide. So if you have the slides printed out, you can follow along if you get lost or have questions that come up. So just kind of a brief overview. We're going to start with the basics of how much water is actually on Earth, go into more detail on what freshwater actually is, then move into why it's important. We'll do a lot of work there on that slide on water usage. Then we'll move into the water cycle and go over some definitions and then kind of how everything is connected in the water cycle. Then we'll move to freshwater ecosystems. We'll go over not only the definitions from more of the technical and legal terms, but also kind of the practical terms. If you are a field biologist, what kind of how you would define some of these systems, because sometimes that differs, and we'll talk more about that when we get to those slides. So we'll go over lakes and ponds, rivers and streams, and then wetlands. And then we will finish up kind of more of the science part of this with threats to freshwater ecosystems, mostly anthropogenic effects, so that's stuff that humans are doing that might affect the environment. And then we will finish up with some resources where I have actually had a lot of success pulling lesson plans and getting ideas for how to teach some of the subjects that we're going over today. So that will be our last point for the evening. So we'll go to the next slide. Okay, so how much water is on Earth? If anyone has seen just a picture of the Earth, what it looks like, you can pretty much tell that a lot of it is water. So it's approximately 2/3 of the Earth's surface is water. And most of that, more than 97%, is actually in saltwater, which we're not focusing on saltwater really today since it's freshwater aquatics. But kind of the take-home message with that is oceans have salt water. That's most of the water that we have access to, but that's actually not readily usable for us. There are technologies like desalination, which can be very expensive. It makes salt water usable, but in general, when you're talking about freshwater, you're more focusing on actual freshwater that's freshwater right now, not water that you can kind of convert into freshwater for later. So that's the big bulk of it. You'll see in that pie chart, 97% saltwater. And then the next part is 2% in ice caps and glaciers. And a lot of times that is kind of referred to as unusable. In a different way than saltwater, ice caps and glaciers are freshwater, but because they're stored in ice, it's not actually feasible to use that, short of going up there with a heater and melting water, which is not really something we can do. It's kind of stuck up there for the long haul. And then moving down to what we kind of refer to as the typical sources of freshwater, that makes up less than 1% of the water on the Earth's surface. And that is split up into two parts. One is groundwater, which we'll talk about more in depth later. That's one of the kind of more conceptual ideas. Because you can't see groundwater, it's underground, as the term suggests. It's a little harder to explain what that is, so we'll kind of leave that towards the end of the presentation. So that's 0.6%, which is found in groundwater. And then less than 0.01% is what's called surface water, and that's found in lakes and rivers and streams. And so for most of what we're going to talk about today, we're going to be focusing on this 0.01%, which is the surface water in lakes, rivers, and streams. So are there any questions kind of about the breakdown of where water is on Earth? Okay, perfect. So we can go ahead and move to the next slide. Okay, so what is freshwater? One of the basic take-home message is it's water that is not salty. In the Envirothon or the Palmer Soil and Water curriculum literature that they have on the website, they have a really good technical definition, kind of refers to how much saline is in the water, but basically it's water that's not salty. And that can be found in lakes, rivers, and streams, like we said before. And then the bottom two, we have groundwater, which a lot of times they refer to it as fossil water. And the reason they do that is because it's so hard to get to it. It takes so long for water to get down underground that sometimes it can be there for thousands of years before we see it. A lot of people might be familiar with groundwater extraction in the form of wells. We have a nice diagram towards the end that kind of goes through that a little more. But it is possible to get groundwater. It's just a little more difficult, which is why it's kind of set aside on its own. And then we have the ice caps and the glaciers, which, as I said on the previous slide, are pretty difficult to get at, but they are freshwater. Are there any questions on that slide? All right, perfect. So we can go ahead to the next slide then. Okay, and here we're going to talk about kind of the common uses of freshwater. So growing up in California, this is a really big topic because we had a lot of agriculture. And a lot of what my undergraduate degree focused in is how you allocate water to all of these different sectors and which ones kind of have more rights to water over others. And that is a very interesting topic, but that's not quite what we're going into today. But we are going to talk about kind of the common uses in each of these sections. So you can think of it as three different sectors. We have the domestic, agriculture, and the ecosystem services. So the domestic usage is everything from drinking water for people to water for household uses. That's mowing or watering your lawn, filling your pool, and a lot of times public utilities also falls under the domestic usage. And then for agriculture, we have kind of two main sections there. We have irrigation, which is water that is used to apply to your crops. There are different types of irrigation. All of them use different amounts of water, and you basically pick your type of irrigation depending on what type of crop you have. Oh, I can keep talking. No, we're on the wrong slide. I'm just going to keep talking while we get the slide back. So the other type of agriculture use for water is for livestock. And that is basically the water that we use to give water for cows, pigs, technically not horses, but that type of thing, so that they can grow and we can eat them. So it's technically still falls under the agriculture section. And then the last one is for ecosystem services, and that's basically leaving water in the system so that fish and other aquatic organisms can be healthy, have what they need out of their environment. And then that also covers recreational usage. So that concept is making sure there's water in there for fishing, so for you to go and fish, or for you to kayak or canoe or boat, just that type of stuff. And before I go to the next slide, I actually have a question for you guys, which is one of those fun facts you learn in all your basic water courses in college. Out of these three sections, domestic, agriculture, and ecosystem, which one do you think uses the most water in the United States? Good job. Everybody who's answered is correct. So agriculture is actually the #1 user of water. In Alaska, that's not really as big of a hot topic, but I will say in California, especially when we have a drought, it becomes a little problematic. The domestic section is the second highest user, but in a lot of places it's kind of shifting a little bit to be more equal. And a lot of times the ecosystem side, even though it's easier for the legal side of the house to kind of work on rights for fish and for recreation, it oftentimes is kind of left towards the end of the spectrum. So before we move on to the next slide, are there any questions on water usage? Okay, so then we will move on to the next slide.
Meg, it looks like you're typing. Did you have a question? All right, I guess not. We're going to move into the water cycle. So we really wanted to talk about this and hit on it. It seemed like it was a large player in the Palmer Soil and Water District curriculum. There's a few driving points that I really wanted to get into on this before we got into each of the 5 components of the water cycle, is that there really is just a fixed amount of water on Earth. We're not really adding or depleting water from the system. It can be in all its different forms, whether that be solid, gaseous, or liquid states, but we're really not adding water to the Earth by any mechanisms, any major mechanisms that would actually, provide a significant change in the amount of water. In order to drive the cycle of water, so it's mainly driven by you need energy to drive any kind of cycle, and this one of the major or the major driver of the water cycle is the sun. It is the big driver and the big producer of all the energy that actually will create this cycle of water from its liquid states to its gaseous states back to a liquid state. So what we wanted to do is we kind of wanted to go over in a little more detail. Yeah. So that chat is kind of distracting. I'm all excited that you get that right, the conservation of energy. Yeah. So we're going to go into the 5 components in a little bit more detail, and we might have I have some verbal activities that we could throw out there for you to try and reinforce some of the components of the water cycle, starting with transpiration. So we're going to go through each one of those in a little bit more detail, and if you want us to stop and go over it a little bit more, or you have any questions, just click the raise the hand button so we're not saying you guys have questions after every slide. So go ahead and go to the next slide, Kathy. So transpiration. This is the process of water getting into the atmosphere, so being converted from its liquid state into its gaseous state. A lot of people in the higher education will refer to both transpiration and evaporation as the same thing, and they call it evapotranspiration, but we wanted to break it up to let people know that there is a very significant amount of water that goes into the atmosphere from the soils as a byproduct of photosynthesis from the plants. I mean, Sabrina had talked about looking at the globe earlier, and we're talking about it's mainly water, but that's all ocean. And then on the land, we've got a lot of trees or plants, and all the plants are doing this. So this is actually the process of the plant drawing the water up from the roots up through and actually emitting water vapor out of the leaves and these little things called stomata out into the atmosphere. And so essentially it's plant sweating. We wanted to put some nice little simple terms for if we have any middle school teachers in here, so they have things that can be reinforced to younger audiences. I had a nice little activity that you could do, because I feel with the younger audiences that it's kind of hard to tell them that there's actually water coming out of the plant, because at least with me, within the particulate world, I have a really hard time visualizing these things. So you can actually just take a clear plastic bag and fix it over, I recommend an evergreen tree, so a pine or a spruce or something like that, and just put it right over a branch and then tape off the end or rubber band the end off, and come back a day or two later and you'll find that plastic bag is actually filling with water. And that's because it's a clear bag. It still allows for the sun to penetrate and allow for the process of photosynthesis to occur, but that water doesn't have any place to go, so it'll actually accumulate within the bag. So I'd like to move on to the next slide if there's no questions.
There's a question here in the chat. Does transpiration cause the movement of water through the soil up through the plant?
It does actually. So there's the first stage is that the water has to go from the soil into the roots. And in order for that to happen, the plants actually, if everybody's familiar with osmosis, which is the movement, the passive movement of water from a higher concentration to a lower concentration. So what the plant has to do is it has to set up a way for the water to move from the soil into the roots of the plant. And generally that's by the plant doing some kind of, physiological stuff. I'm not a plant biologist, but I did take a couple classes. And then once the water is in, it actually works its way up through the stems and the trunk. There's this stuff called the xylem and phloem within the plant. That's where there's water transport and nutrient transport. And it'll go straight up to the leaves. So as the water is evaporating off the leaves, it actually is causing this feedback that is sucking the water up through the plant. You could, in higher level classes, what you could do is you could actually encapsulate the plant within a bag and create the greater humidity within there, so there isn't as much of a difference between the air and the leaf. So there won't be as much passive rates of transfer of the water off into the atmosphere, and you can actually see that those plants will actually take up less water. So yeah, hopefully that answers your question. Being a fish biologist and not a plant biologist.
Corinne, does that answer your question for that?
Corinne, was your question answered? Just say yes or no in the chat. Corinne, you are on a private chat, and so go ahead back to the public, the main room chat. Thanks. Okay, go ahead, Josh.
All right, perfect. Sounds good. All right. So evaporation, as I just kind of talked about with transpiration, is that conversion of water from its liquid form to its gaseous form. In transpiration, it's a chemical byproduct of the photosynthesis. Within evaporation, it's actually the heating of the water so it can actually change its form, its chemical form to become a gas. Most of the evaporation comes from water bodies, so your surface waters. We're talking, and we're going to throw the ocean into the water cycle because the ocean is a large part of the water cycle. But then we'll move on and out of the freshwater aquatics. But so, like I said, this is for the transformation of the liquid water to its gaseous stage. And a majority of evaporation does come from the surface waters. As you can probably imagine, it's pretty difficult for the sun to penetrate into the ground and get groundwater to evaporate. So we're talking from the oceans, the rivers, the lakes, the wetlands, the puddles, any standing body of water that's outside. I mean, you could take a glass of water, fill it up, stick it outside, and mark the outside where the water well was, and come back a couple hours later and probably see a noticeable change in that cup of water, most likely lost to evaporation. So a couple little stats. 86% of all evaporation occurs from the ocean. So all that water is coming up and being evaporated from the ocean as a big budget. And we're going to start talking about some really large numbers here, but I wanted to try and put it in perspective for you. I think most people on here would be familiar with Lake Superior. And Lake Superior is the largest lake in the United States, North America. And there's about 12,100 cubic kilometers of water found within that lake. Now, the amount of water that is evaporated from the ocean yearly is on the magnitude of 434,000 cubic kilometers, which is about 36 Lake Superiors that gets evaporated every year, just from the ocean.
Josh, we have a question here from Brett.
We see
don't we lose a large amount of our snowpack due to sublimation?
Yes, that is true. So in most water cycle kind of diagrams, sublimation is not really one of the traditional processes that they cover, but it is something we're going to talk about more after we go through these basic definitions. So sublimation is the same idea as evaporation, but it's when water goes from the solid state on the snowpack into vapor up into the atmosphere. And it's a little, it is difficult to measure evaporation as well as sublimation. But yes, a lot of the water that we have, or sorry, we're typing and talking at the same time. We do lose a lot of the snowpack to sublimation. But usually snowpack is more measured vertically, not as much, or not vertically, sorry, horizontally, not as much vertically. That is a big field of science. We do have people down the hall who study, the snowpacks and the glaciers, but unfortunately, neither of us are really as familiar with the snowpack side of things as we are with the streams. But I hope that answers that question.
I might add to that the sublimation is like Sabrina said, it's the direct transfer from ice directly to vapor, and that doesn't occur very frequently. It's actually pretty rare for that to happen. Most of the times, the solar energy is actually going to melt the snowpack into water first, into its liquid state, and then it will get evaporated after in evaporation. That's why we actually didn't even include sublimation as one of the subsections, because it is such a small percentage of the water that's actually being going up into the atmosphere in the gaseous state.
Brett had a question about whether of any good activity that could be done, and I'm assuming it's regarding sublimation with kids.
Oh no, like I said, we're not super familiar with sublimation. That's kind of outside of our realm of things. If he was looking for one for just, there you go, something that's for the evaporation, like I said earlier, just put some water in a bucket and mark the level, and then stick it outside for a few hours, and then go back and see where that water level is after. It's most likely going to be lower, and unless an animal comes along and drinks it or something, but it's the loss to evaporation.
And one of the links on the activities and lessons slide, it's the very last slide, is to the EPA, the Environmental Protection Agency. I don't know off the top of my head if they do have a sublimation activity, but that is pretty much the first place I always go when I have to find lesson plans. And the United States Geological Survey, they do a lot of that sublimation type work. They would also be a good resource to go to look for those things.
I see your second question there, Brett. Like I said, I'm not an expert on that, so you might be right. We might lose more of the snow to sublimation, but for me, I just, from observing the physical processes, it seems like more of it is melted into water first, even though there really isn't that much water in the snow. Now you're probably right. It probably is more lost to sublimation now that I think about the actual physics of it. So more to, that's what we have the beautiful thing called Google. We can look this stuff up pretty quickly. So there's no more questions on evaporation. We can move on to condensation.
And Josh and Sabrina, we're at 444, and you are on slide 14.
Okay, so I guess what that means is we need to speed up a little bit. So condensation is the exact opposite. It's the conversion from the gaseous state back to the liquid state, which is by cooling. Like we said, this is all driven by energy. So when the water vapor starts to lose more energy and cools, it goes back into its liquid state, and this is what forms clouds, fogs, and dew. So, don't really need to get into condensation too much. It's just that conversion back to liquid water. So next slide. Well, then we have precipitation. So once it's cooled back into a liquid state, the clouds can actually become too heavy and lose their water. And that, like we said, we're all very familiar with precipitation. We see this, especially in Alaska, pretty much daily, except for that snow. That's kind of a lost thing here this year. But the precipitation can be in multiple different forms, like the diagram shows: snow, freezing rain, hail, rain, and basically, like we said, that's when it comes back to its liquid stage and comes back and is precipitated out of the clouds back to the earth. Obviously, this isn't all in liquid state as snow, and both, freezing rain can be, or sleet can actually be in the solid state of ice. You move on to the next one. So accumulation is basically the storage of precipitated water. So far we've talked about it leaving the ground via either transpiration or evaporation, going up into the clouds and then coming back down. So this accumulation really kind of completes the cycle that we've been talking about, the simplistic cycle. So it's just the storage of that precipitated water in the surface. So it's going to be the ocean. Obviously our ocean, there's our major storage area like Sabrina talked about earlier. Then we have all the other places that the water can accumulate. So the lakes, rivers, ice and snowpack, and the stuff that actually percolates down into the groundwater as well, which, as Sabrina said earlier, is our largest source of fresh water in the world. So a lot of it actually does go down and get stored in the ground and can spend thousands of years down there. So next slide, if we don't have any questions.
Okay, so for this last slide on the water cycle, we wanted to kind of put kind of more of a picture to all of these definitions we've been talking about. And I was going to go through all of the definitions again, but for the interest of time, I'll just briefly kind of say the definitions as we go through. So a lot of people like to start the water cycle in the ocean. I was taught to start in the mountains, so that's where I like to start it. So if we look at the top left, we have water that has been stored in ice and snow. If you remember, that was about 2% of our water in the water cycle is stored up there. And we do lose some to sublimation, which, as we kind of talked about for a little bit earlier, is when the snow turns directly into vapor. And what we don't lose up there, we lose in what is called snowmelt runoff. That happens when the snow starts to melt, and runoff is basically water that's not going down into the ground. It's kind of moving with gravity along the surface down. This is overview. This is a watershed. So all of the water that's kind of affecting the system is all contained into the one watershed. So the snowmelt is going down the watershed. Some of it is kind of percolating through the riverbed into the groundwater. And what's not doing that is moving down through stream flow. So it's basically just water that is physically moving through a river or stream. Some of it's being accumulated in freshwater storage. That can be a pond or a lake, sometimes a river. Some of that water, because it's surface area, it's being evaporated from the freshwater system. And if it doesn't evaporate or kind of go into the groundwater throughout that part, it can also then flow directly into the ocean. So we also have the groundwater on the bottom left. That's flowing into the ocean as well as flowing into the freshwater storage. So now we have water. It started in the mountains. It either went down into the ground, or it flowed downhill into a freshwater storage, or it moved down into groundwater out into the ocean. And then we have water in the ocean now, so we're at the bottom right. Some of that water is evaporating up into the atmosphere. We also have water that is going through evapotranspiration, so that was evaporation plus transpiration, which remember is the plants that are sweating. So that water is going up into the atmosphere, condensing into clouds. And when the temperature and the amount of water in the clouds, so the density in the clouds gets just right, the rain droplets form, it gets too heavy up there, and then they come down in what is called precipitation. Some of that water then runs right back off, starts the cycle over, and if it's cold enough, some of that water goes back into the ice caps, the glaciers, becomes water stored in ice and snow again. So that's kind of an overview of the water cycle. Usually I have pointers and things, animations to kind of follow through, but did that make sense to everybody? Okay, looks like it. Yes, thank you. So that is kind of putting a face to all of the names that you just learned, and we will move on to the next slide.
So we wanted to cover some freshwater ecosystems as well. Basically, we've kind of already talked about a lot of these with going through the cycle, but at this point, we're really just going to throw the ocean out of things and really just talk about, that 2% essentially of fresh water that's found on the earth. So we have several different kinds of the lakes, ponds, rivers, streams, wetlands, and groundwater that you're all kind of familiar with. We're going to do some characteristics of the freshwater ecosystems, so like a lentic versus a lotic system. We'll just define that right now for the sake of time. Lentic systems are any surface body of waters that don't have flow to them, so your lakes, your ponds, and some of the wetland habitats like bogs or lentics, there's no flow associated. And the lotic systems are ones that do flow. So that's going to be your rivers, your streams, your groundwater. And then we're going to, within each one of those kinds of the ecosystems, so lakes, ponds, rivers, streams, we're going to talk about some habitats there, and then just pictures of common animals, interactions, and these are going to be very Alaska-based examples, because that's what Sabrina and I both work with or most familiar with. And then finally, we're going to finish with just some anthropogenic threats to freshwater ecosystems. So we can move on to the next slide.
Okay, so before we go into each specific environment and habitats that go along with them, we're going to kind of first do an overview of what the actual definitions of those things are. And like I said kind of in the overview slide, a lot of times when you look at the policy or the technical legal definitions of these things, it can be different than what you might refer to in practice, or even really what a lot of management considers to be, for example, a lake or a pond. So I'm going to do my best to kind of cover both sides to give you an idea more accurately of what these things are. So a lake and a pond, the technical definition is a large body of water that is surrounded by land. Technically, a pond and a lake is kind of considered the same thing, but in practice, a pond is a smaller lake. A lot of people use this, what you can kind of refer to as the can you see the bottom test. So in general, a lake is usually deep enough that you cannot see the bottom of it, and a pond is shallow enough that you can. But be a little weary with that, because sometimes there are lakes that are very deep, very large, but are so clear that you can see the bottom. And there are also ponds that are shallow where you should be able to see the bottom, but because they're so murky or turbid, you can't. So that is kind of the overview of those two definitions. And we can go to the next slide.
So before we get into the lake and pond habitats, quick question for the group. Are lakes and ponds lentic or lotic systems? Excellent. People are actually paying attention. I love it. So we have so basically this diagram right here is just kind of showing the different zones within a lake or a pond. Now I'm going to start with the bottom, which they call the benthic zone. So that's basically anything that's associated along the bottom of the lake or pond. That can be the bottom at 300 feet of water, or at the bottom of 3 inches of water. Anything that's on or associated with the bottom is the benthic area, and that can be a small area also above the bottom. But there's a lot of fish species and macroinvertebrate species that are associated with the bottoms of these water bodies of water. One big thing that a lot of people like to leave out of any habitat analysis, especially aquatic ones, are the influence of terrestrial plants on these systems as well. They actually do provide a lot of benefits to these aquatic ecosystems. With large trees, and I realize the diagram doesn't have any trees, but they will shade the water, so that actually has a cooling effect. So there's some thermal refugia for fish or whatever. There's also a lot of the deciduous trees, so the trees that lose their leaves, when these fall into these aquatic systems and then decompose, they actually add valuable nutrients to the systems as well. So terrestrial plants really are part of the habitats. So then you can see that next zone kind of moving offshore is called the littoral zone. And basically the definition of the littoral zone is all like the near shore habitats that are found within these bodies of water. The best way to really define it is it's the areas that plants can actually grow. So it's shallow enough where there's the submerged plants that they actually can grow up and we can see them. That's still the littoral zone. As you move out past that, you get into the limnetic zone, which is really an area that doesn't have a lot of underwater plants or submerged plants growing in these areas. However, you can still see that the diagram there that there's the vertical line talking about the euphotic zone, which actually still talks about the amount of water that light can penetrate. And depending on the turbidity and all kinds of other factors, the general area for a euphotic zone is about 100 meters, so a little over 300 feet is about how far light can penetrate before it becomes super dark. So that's kind of what they're talking about there. So then we have all the different zones of these lakes and ponds. So we move into the next slide, and I want you guys to really remember those zones. So as we talk about the animals that are there, we can kind of identify the areas that they're in. So realize there's no actual tags with any of these, but we'll start in the upper left. That's just a picture of some plankton. That's the base of the food chain. Not only that, we have both phytoplankton in there, which would be the little green guys that you see kind of in it, and then we have the larger ones, which is the plankton. This is really the start of the food web within any lake or pond system. These guys are free floating. They just kind of hang out. They're going to be in that limnetic zone that we were talking about, because the base of the food chain is the phytoplankton, and the plankton eat that, and then so forth. We have macrovertebrates that will then eat the plankton, or even a lot of these other fish species will eat plankton before moving up. But really want to emphasize that this will be found pretty much throughout the lake, littoral zone, and the offshore zone. But it has to be they're really isolated to only areas where there is good sun penetration, or else they will die. And top middle there we have a macroinvertebrate. These guys within lakes and ponds are generally associated with the benthic zone, which is the bottom. Sometimes they'll be found on some of the submerged plants, crawling on the stalks or whatever, but these guys are feeding on the lower level organisms, so the plankton, and associated with the benthic. But then we have, really kind of like the next one's a duck. I mean, I'm pretty sure we're all familiar with ducks. I threw a duck and a loon on here because they actually both kind of feed on different things. The mallard will feed more on bottom detritus and plant material and some of these macroinvertebrates, maybe some small fish, while a loon is actually more of a piscivorous. Piscivorous is not right. That's a fish-eating bird. Piscivorous is a fish-eating fish. So I used that term incorrectly. So the mallard you're going to find more in the littoral zones of these lakes, so that they can, you see them dabbling with their feet up in the air, their head down, while they're kind of digging around in the benthos, so the benthic part, trying to dig up little worms or other macroinvertebrates. While the loon could be found actually outside of that area where there are still some fish, as it's more of a diving species that will go after smaller fish species. We also have a couple, the two guys at the bottom are both fish species found in Alaska. The one on the left is an adult sockeye salmon. The one on the right is a lake trout. And I threw those in there so that we have a couple examples of fish species that kind of use different habitats within the lake. The lake trout is really a benthic species that is mainly found in very, very close association with the bottom. And that's because it really likes cold water. And in lakes, the coldest water is actually found at the bottom of the lake in the summer. That's because of how the properties of water and how water is actually densest at about 4 degrees centigrade. So when it's at its densest point, it then will fall to the bottom. As water cools beyond that, it actually becomes less dense, just because of the physical properties. And as they go, they'll move up into the, that's how ice can form on top rather than the bottom. Cool. We can, yeah, next slide then. I'll just jam through these.
Okay, rivers and streams. Technical definition is that is a large natural watercourse that flows to the sea, a lake, or a larger stream. In practice, a river is a larger version of a stream, which is a larger version of a creek, but a lot of times those things can be interchangeable. And Emily, we see your question. Terrestrial plants, do you mean riparian zone? So a riparian zone is actually good to talk about with rivers. That's the area that's on the land that's touching the waterway. And terrestrial plants can be found in a riparian zone, but also in the
so basically the plants you're going to find in the riparian zone are plants that actually have a little more tolerance for large amounts of water. As you move upland and you increase in elevation, you're going to have less and less water in the soil. And so a terrestrial plant is really one of those plants that can't, it just can't survive in those lower lying areas where there is excess of water. So the riparian zone plants will be ones that actually do really, really like water a lot. So we're going to hit the next slide. We're going to jam through these for you guys, and then we can just answer questions at the end. So rivers and stream habitats, basically the big ones that you need to know are the pools and the riffles. The pools are these little deeper areas that are, the water moves a little bit slower. It's a really good fish habitat, especially for juvenile salmon. And the riffles are areas where the water really shallows out and there's a higher gradient. So what I mean by that is there's a greater change over distance in the elevation. So the water will actually move faster, and this is where oxygen is brought into the water, but this is also areas where the bottom is agitated more and will actually release nutrients and release macroinvertebrates into the drift down into the pools where the fish and other guys will eat them. There are a ton of other river and stream habitats, but those are the two big ones that I feel like everybody needs to know. So next slide. So what I wanted to show you guys here is, notice I kind of took plankton out. Plankton are still part of river systems, but they're not nearly as important. It's more algae and other smaller single-celled plant organisms that form the basis. But within rivers and streams, we have a much higher abundance of larger macroinvertebrates that are working the bottom that will actually become part of that drift for some of your fish species that you can see at the bottom, with like a rainbow trout or coho salmon. I had to throw it in there. That's my specialty. But we also have other animals in here. In the upper left-hand, that's a caddisfly. Those things are actually really cool. You can see that they got the pebbles. They actually create their own husk around them. They can make them out of plant material or stones or whatever. And there's actually this upcoming theme where what they're doing is they're throwing caddisflies into fish tanks that have like gold and actual like diamonds in the bottom of them, and letting the caddisflies build these husks that they then harvest and turn into earrings, which is just really kind of cool. But we gotta move along because we're running out of time. So next slide, please.
Okay, and the final freshwater aquatic ecosystem we're going to talk about are wetlands. Wetlands are a little more defined in the legal side of things because a lot of people like to develop on wetlands. But in general, a wetland is an area with land that is wet and spongy. It's often a marsh, a swamp, or a bog. So in a lot of times, you can classify wetlands by how often they're full of water or how much they're connected to other rivers and streams. But the big take-home message with the wetlands is that they're wet and soggy most of the time. Next slide. Okay, so wetland habitats. The big important thing about wetlands is that they're not like the other systems where they're just full of water, large amounts of water. They can kind of change. But in general, a wetland habitat has 3 different zones. They have the aquatic zone, which is the part in the middle. That's the part that's actually full of water. So if you have, for instance, a wetland that's more like a pond, that's going to have a bit of water. just actually sitting in it. A lot of times the water is not moving, it's just kind of sitting there. So that's the aquatic zone. Then you move up to the riparian zone, which we talked about a little bit before with Emily's question. But that's the area that's touching the aquatic side, but it's technically not underwater. A lot of times the riparian zone, though, can be really moist. The soil can be wet. Sometimes there might be water that's kind of sitting there. And a lot of times with wetlands, these zones aren't as cut and dry as in some of the other areas, because depending on how much water we have, how much the streams that might be connected to a wetlands are full, those zones can kind of shift a little bit. But in general, we have the aquatic and then the riparian. And then further up from that, we have the upland area. Those are areas that, for the most part, they do not fill with water. They're a little drier with the soil, and that's where some of those terrestrial plants that you had asked about would be found. So this is a good diagram to kind of conceptualize Emily's question from earlier. Next slide.
So let's take time. We'll just kind of really quickly move through this. You're going to see a lot of the same animals that you can find in some of the lake and pond systems that are also in wetlands. There's a lot of the lakes and ponds actually form these wetlands with the overflow, when the like the slow-moving or meadow streams or whatever. But there's a nice example, and I mean, a couple of these are probably really familiar to the Alaskans with the mosquitoes and the gnats and all that other good stuff that we all come to love in the summer. But you're going to notice that the fish species I threw in there are a little more different. They're ones that actually like to live in vegetation. And the big thing with wetlands is most of them are so shallow that they're pretty much all littoral, especially in the standing water bodies. So you're going to find a lot more species that are plant-loving within there. As you can see the muskrat in the bottom left-hand corner, or the grebe that actually needs all that stuff, needs that vegetation to nest for its babies. And then fish species that actually hide, that are more stalking predators like the pike and the blackfish that are pictured there, that will actually hide in the weeds and then jet out and grab something really quick. So next slide. So some anthropogenic threats to freshwater. I was going to talk to you guys about some eutrophication, which is basically the chemical enrichment of these water bodies. So this happens more in lakes and ponds, because they are standing waters bodies. However, the rivers can become eutrophic, can undergo the same process, but they mainly are the drivers that actually bring the nutrients in through runoff. So we're talking about excess amounts of nitrogen and phosphorus that can get into these systems. These can come from, mainly coming from non-point sources, which is on terrestrial land. So when we add a bunch of fertilizers or anything else to the land, it will actually run off into the water bodies surrounding it, such as your rivers or streams or your lakes, and then accumulate. And when you accumulate nutrients, the algae and so the primary producers, the algae blooms and the phytoplankton and stuff, they can get out of hand. There's nothing limiting them anymore. So they have all the nitrogen, all the phosphorus they need. The sunlight's still beating down, and they'll grow and reproduce at such extreme rates that they actually can choke out the system. They can block the sunlight to other organisms. But the real big issues that happen here is when all that stuff dies off and then goes down to the bottom and starts to decay. Whenever anything decays, it sucks all the oxygen out of the system. So these lakes become highly hypoxic, which means there's no dissolved oxygen left in the system, which would kill just about everything, because all living organisms essentially need oxygen. So eutrophication in a nutshell. Next slide, please. So we have water quality sampling. I threw these in here because these are all great for, we threw this in right after eutrophication because we use a lot of these instruments to measure stuff like that. So in the upper left-hand corner, you see a Secchi disc. It's basically a disc that is lowered down into the water. That rope will have a measuring tape on it, so you can actually see how far down can you actually visibly still see that BMW sign in the water column. And that is just a good measure of how turbid the water is, so how many suspended solids are in the water. Directly below that, you see a tidbit temperature logger. I use these quite a bit with my stream studies with the juvenile salmon, looking at thermal refugia and thermal regimes within the streams. So basically these things, you just set them in the river and they record a temperature every minute, every hour, whatever you set them to do. And then we can go in, we can download them, and then it will actually spit out all the data for us and all the different sites. In the middle there, the two pictures, they're actually the same thing, and this is what this is a sonda. This actually will pick up multiple water quality measurements, and we also use these in stream as well. The sonda, like Sunday, it measures multiple water quality measurements, and we actually have one of these sitting in stream as well year-round, just checking all the different measurements you can see on there. So turbidity, just like the Secchi disc, pH, so how acidic the water is, the amount of dissolved oxygen, the specific conductance, which is how many ions are in the water. So what most people don't know is that water, pure water, so purified water, or not purified water, I'm sorry, distilled water, is actually an insulator. Most people think of water as a conductor, like, oh, well, I could put electricity in the water and it will shock me. Well, if you have distilled water and you put electricity in it, the electricity does not transmit through the water. The only way that it can transmit is on these ions that are dissolved in the water. So that's what the conductance is actually measuring. And the last one I wanted to show you, which I was really glad I threw this on here because it looked like there's a bunch of people that were interested in macroinvertebrates earlier, is that a good way to test water quality is to actually look at your macroinvertebrate in communities within lakes and rivers. And depending on the community that's there, you can actually tell how degraded the system is. In areas where there's a lot of damage been done to the system, only certain macroinvertebrates can live there. So if you have a higher diversity of the macroinvertebrates, you actually have a healthier system. So that's really what I wanted to convey on this water quality sampling slide. So probably next slide, please.
All right, so the final kind of slide for this to wrap it up is talking about groundwater extraction and pollution. And I also have an activity that I've had a lot of success with in the past that I can share with this slide as well. So again, a basic overview. I've kind of hit on these things throughout the talk, but just to put it on perspective, what is a groundwater system? So if you look at the picture on the left, we have clouds that are raining. That water is percolating or infiltrating through the soil down into what is called the water table. And this picture is not the best to show what it is. Usually there's just a picture of a blue line that goes across, and that's where the water table is. But in this picture, it's probably more accurate as to what the real system is like. All that area with all the blue speckles, that is kind of the water table / groundwater aquifer, which is another term for kind of like the storage bin of the groundwater. So you have water that's moving vertically, going from the top down into that system. It's also moving horizontally, and that's kind of done through what's called capillary action. That's where the pressure is sucking that water towards the empty spaces and moving it out into the stream. That thing in the middle is actually supposed to be a stream. So that's what we call groundwater discharge. So that's kind of how it moves through the system naturally. And then we also have a well kind of built on that left hill. And that's what you do to get water out of the ground so that you can drink it or use it for irrigation usually. And so you build actually a well. It goes right down into the water table. It sucks water out. And a lot of times what that does is it sucks so much water out that the water table actually lowers. And you get what's called a cone of depression, which is where the ground starts to sink where you've taken all that water out. That happens a lot. If you have too many wells that are drilled into the same aquifer, you can actually suck it dry, is what it's called, sucking the well dry. And there's no more water down in that system. And so that's kind of a brief overview of what groundwater is and how it works. And pollution is a big problem with this because not only does water fall through the system, but pollution can also do that. Chemicals, there's like any ag runoff or arsenic happens a lot. It just moves down with the water and gets into that well, or not into the well, into the groundwater system, into the aquifer. The well can suck that up. Now your drinking water has chemicals in it. Or that water will eventually kind of go out into the stream as well, which causes a whole set of problems. There's no way to treat your water when it's down in there. You can only treat it when you pull it back up. And so kind of an activity that I've used before to kind of show this is if you take two plastic cups, two of the clear plastic cups, and you drill a hole through one of them, and you put the one with a hole inside the other one. That's kind of illustrating kind of more of the surface is the cup with a hole in it, and then the bottom cup is the groundwater aquifer. And you can put, you can do this with like chocolate or gummy worms or candy, or you could do it with rocks and things that kids can't eat. But you fill that bottom cup with different rocks. That's supposed to kind of illustrate what the ground is actually like. You put some water into the top cup. That water will kind of go through the hole you drilled and sit towards the bottom so kids can see what groundwater is supposed to look like after it kind of percolates through your pretend substrate. And if you take some food coloring or chocolate syrup, people do that with chocolate syrup as well, and you then pour that down into the top cup, you can see how pollution kind of flows through your groundwater system and taints all of what used to be clear water at the bottom. You can also use that with milk and chocolate milk. And so a picture to illustrate that is on the bottom right. This is actually a picture of fracking, which we aren't really going to go into, but you can see how when you drill something down past the water table, in that picture the blue line is the water table, it's very easy for you to get chemicals in that system, and once it's in there, that's where it's staying. So that is kind of the last point in the groundwater section, and we can move on to the next slide.
So we didn't really want to reinvent the wheel here. We just wanted to give you guys some links to a bunch of different activities related to freshwater, and this is just ones that we found incredibly quickly just with a quick Google search. So if you're looking for anything else more specifically, you can probably just do the same and be able to find those. But right after Sabrina talked about groundwater, I know we had that question earlier about seepage lakes, and that just seemed like the perfect transition to talk about seepage lakes just for a second. So basically, for those of you that don't know, a seepage lake is a lake that has no surface inflow or outflow to it. So there's no river or stream that's going into this lake and then filling the basin with water. The only way that seepage lakes form and are maintained is through groundwater recharge. So it's actually water that's seeping out of the ground into these basins and keeping them full. So if you have a seepage lake that is actually slowly declining in level through time, it's because the groundwater is actually slowly decreasing through time and not recharging that lake at the rate that it needs to, that it's losing its water to evaporation. So hopefully that answered the question for seepage lakes, and we can talk about them a little bit more. I'm not super familiar with them, even though I work with a lot of them. It's more of a geologist type of thing. But with that, we're going to conclude and open it up to any questions, and we apologize if we went way over. We're just a couple nerds that love to talk about science.
That's not a problem, Josh and Sabrina. So we'll pause for a minute to see if people have other questions, and I see Brett has one there. How do you deal with currents when using your sticky disc?
All right, so a Secchi disc, we only use those in lakes and ponds. I think that they do use them in the ocean as well, so we might run into some more currents there. When we're talking about when we're taking you know, turbidity measurements in stream, we actually use this sonde that I had showed the picture of. So, all right, well, in the ocean, if that's where you've had your issue, a lot of the Secchi discs, they don't look like much because they just look like a little piece of plastic, but the ones that we've used are so heavily weighted that it's not really an issue. It just kind of falls straight down. I mean, it might turn it slightly sideways, but you're still going to be able to get that really contrasting image. So you should be able to still see them and not have them like really pull them away. I mean, if that's a serious issue where it's actually pulling away at an angle, I mean, you can actually just, you know, do a squared plus b squared equals c squared, and then actually figure out the appropriate depth based on what's going on there. Yeah, exactly. Halibut weights. that works.
And Janet has
So
suggested.
I thought about it a little bit more while we're doing this.
Go right ahead.
I thought about it, and I can't remember exactly. Oh, it was Brett. He was talking about the sublimation, and I actually thought of an activity just here on the side because I was so embarrassed that I didn't know enough about it. Is that you could take a couple, so Brett, you could take a couple containers and pack them full of snow, because they're going to have this, the same volume. Make sure they have the same volume. Pack them both full of snow. Cover one so water can't escape, and then leave the other one open. And then what you'll be able to do is let it melt down to the water stage. And what you'll see is that the one that was open that actually allowed the water to escape via sublimation is going to have less water less water volume in that cylinder than the one that you cover that doesn't allow any evaporation or sublimation to occur, just with the melted water. You have to keep a quick eye on it so it's not like sitting for a while after it's melted. But I mean, or you can just don't add heat because that will add a whole another factor. But just let it sit out at room temperature, and you should be able to do that within. I would think if you started it in the morning, the snow would be melted by the afternoon. So just want to throw that out there.
Thank you. So Janet has put up a contact, Betsy Wilkening. She's with Arizona Project WET, and there's a link there for other great ideas for classroom activities. Any other questions? Well, first I'd like to thank Sabrina and Josh very much for a really fun presentation. Not to worry that it went over. I'd say everyone stuck around because it was going so well. And I'd like to thank the rest of you for coming today. We're going to connect again in 2 weeks on Wednesday, March 18th at 4 p.m. once again. Our next speaker will be Beth Trowbridge, and the topic is Intertidal Ecology Life on the Edge. So with that, I'd like to thank you all very much, especially Josh and Sabrina, and have a good evening.
Thank you all for joining us. We really
Thank you.
appreciate it.
Good.